So thank you, Chairman, and I thank the organizers. I hope they are all in Hall 3 now for the kind invitation. The original title of my talk was Novel Heterostructures of Ironicidides. However, I would like to present a more general view on iron-nictide heterointerfaces. And my co-authors on this are Ian McLaren and Masato Sasase, who are doing excellent TAM work. Michiko Sato, who was responsible for the Auger electron spectroscopy depth profiles, and for the theoretical calculation, we collaborated with Sergei Nikolaev. I would like to introduce also my recent book on iron-based superconducting thin films, which was published this summer, and you will find the content of this talk basically also in that book, and finally also in a recent article in MPG Asia Materials. So let me briefly introduce iron-nictide thin films and pulsed laser deposition. Since 2008, we have faced the discovery of many iron-based superconducting compounds. However, if we deal with thin film growth and we choose a particular growth deposition method like pulsed laser deposition, we see that only a handful of compounds have been grown and studied successfully. And this has several reasons, and one of these reasons is that the method itself faces limitations and difficulties, for example, in the presence of volatile elements or when we want to grow ultra-thin films. There is no need to give up at that point because we can apply so-called interface engineering concepts also to the iron-nictides. And in the past 5 years, there were mainly two advances within that field. One was using diffusion and bringing the so-called volatile fluorine from the substrate into the as-grown films in an in situ PLD process of the samarium iron oxynictide thin film. And this was shown in 2016 and maybe in one of the previous ICSM conferences by me. Another approach has been adopted by Aeon's group is the so-called strain engineering, and here barium iron 2 arsenic 2 STO multilayers have been grown with different thicknesses, and what you can see on the right side in the phase diagram is when you decrease the thickness of the barium 1 to 2 layer, you can change and tune the arsenic iron arsenic bond angle, and by that you can change the electronic state and induce superconductivity. However, both approaches have not focused on the fundamental aspects of the iron-nictide heterointerfaces, and this is now done by this new classification which we have proposed now recently in MPG Asia Materials. To motivate this classification, let's look on the iron-nictide structure, which are layered polar compounds, and the layer has a layer charge of -2 here. So this is very different from the iron selenide, which are not polar compounds but van der Waals compounds. Here we have an ionic bonding in z-axis lattice direction, and you can see the alternating layer charges of minus and +2. So this is what iron-based or the iron-nictide superconductors are comprised of. So if we remember the classification and stability of ionic crystal surfaces, we can have 3 types according to the Tasker classification. So in type 1, the ionic crystal surface is neutral, so we have a balance of charges, so the total layer charge is 0. In type 2, we can have an individual layer charge. Within the unit cell, we have a symmetric arrangement. That means we do not possess any electric dipole moment. However, the nictides are made of type 3, and we have here an individual layer charge, and this individual layer charge is alternating, and so we do have electric dipole moment here. So this, of course, with that knowledge, we can go into the literature and search for different iron-nictide hetero interfaces which have been studied. And we found a couple of examples, for example, the barium 122 on STO. And here we have to face two different terminations. So here is the titanium oxide terminated STO, and the barium 122 is grown on top of it. And you can see here we have a unit cell of a mixed barium strontium titanium oxide interface layer which forms. And what is also seen that it was also reported that the titanium valence changes from 4+ to 3+ when we go towards the interface. The situation is similar in the case of the strontium terminated STO, where we have barium iron 2 arsenic 2 grown on top of this strontium oxide terminated STO. Here, however, the interface layer is much larger. So we have here a barium iron oxide interface layer, and it is much thicker. As you can see, several unit cells are thick, and this is because we have here a valence change of the iron, and when going from the top near close to the barium iron 2 arsenic 2 down to the bottom, we see the valence change from 2+ over 3+ to 4+. We find also an interface layer reaction in the case of barium 122 on LSAT. Here the situation is a bit different. We see here a metallic iron layer which is formed at the interface and some kind of barium diffusion into the LSAT. However, this interface is not well resolved. So we can summarize all these examples as layers where we have as hetero interfaces where we have interface layer formation, and we can call them initial uncompensated interfaces. That means the interface tries to compensate the layer charges and the dipole moments, and this is done via the valence change or the compound formation or via the metallic iron layer. So the question is, can we draw also clean interfaces? And we can do that if you think about the example of barium 122 on directly on iron. We see here that this is a clean interface, and the interface is located at the iron planes. There's a commonly shared iron plane. And this is not the only example, so we can call that clean interface initially compensated interface, and it is also coherent due to the lattice matching. But this is not the only example of a clean interface, so we can also have a polar compound on a polar compound, so two iron nictide compounds on top of each other, which demonstrate the same principle, so that we have a clean interface here, and the interface is located at the iron planes. So let me summarize the classification of iron nictide hetero interfaces. We can divide them into initial uncompensated ones, which lead to a compensation mechanism and which is responsible for the interface layer formation. And we find that when we grow the iron nictides on nonpolar oxide materials like STO, LSAT, and I will show later on some example on NGO. We can have clean interfaces, which we call initial compensated interfaces, and this is when we grow these iron nictides on metals or polar materials. And you have seen the examples of iron, and I will demonstrate then the example of iron nictides hetero interfaces. So this classification helps to predict the microstructure. It is useful as an engineering tool for thin film engineers, but it is also valid for impurity phases and defects in any solid, so also in the crystals. So let us now go to the new polar iron nictide hetero interface, and we now join the iron oxynictide on top of the barium 122 layer. They have this commonly shared iron 2 arsenic 2 layer, And when we calculate the local potential and the average, we don't see any, we see basically a smooth variation of the average local potential. So this should be a stable and clean interface, and this is what we indeed have observed. So you see here 3 panels, so a TEM image, an Auger electron spectroscopy, depth profile, and the result of a resistivity measurement on that bilayer structure. And you can see here that we find indeed the interface at the commonly shared iron plane. You see also in the Auger electron spectroscopy that the interface is very sharp. We can really distinguish the iron oxynickdite from the 1 to 2 layer. And because this film is undoped, we do not expect any superconductivity here. And this is what we measure actually. So we can test now the stability of this interface by adding impurities, and we have done that by adding cobalt cations or oxygen anions. So when we add cobalt cations, so cobalt 2 plus, into the target material, so we have started now the growth with the iron oxynickdite cobalt dope target. We grow again this bilayer on top of undoped barium 1 to 2. We again find that the interface structure is clean, and we have a smooth and very sharp interface at the iron common iron plane. So the interface, the cleanliness of the interface stays intact. However, we see that the cobalt diffuses from the top layer into the bottom layer down to the substrate and leads to electron doping as we know it from any bulk experiment. Finally, we also see that we can measure a TC of almost 17 Kelvin, so the cobalt concentration seems to be balanced within both layers. The situation is completely different when we have an imbalance of anions. And here you see a very good example of cation-anion asymmetry. So if we add additional oxygen anions here in the deposition of the upper layer, we find that the upper layer is partially consumed by the interface layer formation. And you can see also the interface layer formation. It is about 10 nanometers thick, so it's quite large here. And you can see that clearly also in the Auger electron spectroscopy depth profile, where we have a strong decrease in the arsenic content, and we have basically all the additional oxygen, and the oxygen imbalance is swallowed up by the interface layer. Interestingly, this bilayer with this interface layer shows an induced metal to superconductor transition with a quite high superconducting temperature of 28 Kelvin. So let me just say a word to this induced metal to superconductor transition, which is now under investigation. Here again, this is the interface layer where you see also in the bottom part of this image the EDS mapping for the different elements. So and you see there's a lack of arsenic, and this interface layer consists largely of oxide phases. So we have a samarium oxide phase and possibly also the iron oxide phase here in that interface layer. So how does this superconductivity arise is still under investigation and a big puzzle to us. We think that this is also due to some kind of diffusion process which is going on. But what we can say is when we measure the angular dependence of the upper critical field, is we definitely see a 2D behavior. So we can fit here a Tinkham's formula and see that there is the superconductivity is confined in the layer, and it should be the upper layer here. This is in contrast to the cobalt doping again, here where we see the cobalt is diffusing from the top layer into the bottom layer down to the substrate. We finally see a 3D superconductivity state. So we have here the Ginzburg-Landau classical formula for 3D superconductors. So in the last section of my talk, I would like to share some information about another heterointerface between the barium 122 iron nictide and MgO. And I would like to show you how this interface is changing or influencing the film roughness when you go to ultra-thin films. So we grow the barium 122 on MgO, which should be an initial uncompensated interface. And in addition, there is also a large lattice misfit within this system. So our result will be that we will find a heterogeneous interface here between these two compounds. So one type of the interface is barium rich, and you can see that clearly that we have here additional barium layers between the barium iron 2 arsenic 2 unit cell and the MgO, which cannot be resolved unfortunately due to this strong contrast here, but you can see clearly that we have here additional barium layers of barium atoms. In addition, the TAM-EDS mapping shows also a large fraction of barium at the interface, so a very strong barium signal there, and a lack of arsenic and a decrease in the iron. On the other hand, we also find an iron-rich interface, so we can find sometimes at the interface that there are iron islands formed, and these iron islands form then the, as already known, 122 iron interface, which is also a clean one then. So both interface types will now, so I will now show you how this two interface, or this heterogeneous interface, is basically changing the film roughness when we increase the thickness of the films. So you see here a series, a thickness series of 5 films, and here the AFM images of the surface topography. And what we can see here for the very thin film is that we have a very strong island formation, whereas after a certain threshold thickness of 30 nanometers, the film seems to be continuous, and the surface roughness is governed by mount formation of the multi-layer growth. So here are the thicknesses as determined by the X-ray reflectivity. So this is the total thickness by the X-ray reflectivity. However, we can also determine the coherently grown volume by the lower fringes. So when doing so, we can map here the situation in a sketchy graph. And what we find here, and what you can see here, is that we have in all the films a part of an interface layer which is not coherently grown barium 122. So this is this gray section at the interface, and this can shrink if you grow the films thicker and thicker. Finally, you see also that in the very thin film limit, in that configuration here, the surface roughness is mainly determined by the peak-to-peak roughness of the islands. And only after you reach a threshold thickness of the 30 nanometer, we will finally have the roughness of the film is close to the RMS roughness due to this mount formation. So with this example, I would like to thank you for your attention, and I conclude my talk. You have seen now a new classification of iron nictide heterointerfaces, which is based on electrostatic principles, and we can classify the heterointerfaces into clean ones, which are initially compensated interfaces and which appear at the iron planes, or interfaces that show interface layer formation. These are the initial uncompensated interfaces. You have seen that the superconductivity in the iron nictides can be controlled by diffusion We can also see metal to superconductor transitions with quite high TC of 28 Kelvin. And finally, I have shown you an example of a film substrate interface and how it determines the film roughness in ultrasound films. Thank you very much.
Thank you very much for the nice talk.
So you didn't mention that any dependence on temperature of the substrate at which you grow the structures. Is there any dependence or limits for upper temperature or lowest temperature for that, such a nice interfaces? Thank you.
I repeat your question because I'm not sure if I got it. So you are asking the substrate temperature during film deposition. That was correct? Yes. Okay. Yes. So in the case of the iron nictide thin films, we use quite high deposition temperatures. And these deposition temperatures are in the range of 850 degrees C. So if I grow these bilayers, for example, the iron oxynictide on the barium 122, so the substrate temperature, the substrate layer was MgO, and the temperature was during the deposition constant at 850 degrees C. When you grow the barium 122 on MgO alone, you can decrease a little bit this substrate temperature. However, it was maybe similar to 800 to 850.
Okay, then I have one question. Maybe I missed the point. In the first part, you presented the heterostructure of 11 system and barium 1 to 2. And which one is responsible for the superconductivity?
We have two types of heterostructures. One type of heterostructure, or maybe I show you that one. One type of heterostructure is a clean interface, and this clean interface is not altered by adding cobalt. And when we add cobalt, so cobalt is known for electron doping. It can electron dope the iron oxynictide, and it can electron dope the barium 122. And in both cases, we have a doped layer, the upper layer and the bottom layer, and the superconductivity has signatures of a 3D superconductor. So we can assume that both layers are superconducting and share just the average TC. In the case of when we have the oxygen imbalance, we find interface layer here, and we also find this induced metal to superconductor transition. And you can see here in this graph of the resistance versus temperature, we measure that that becomes superconducting after 50 days. So this is quite long. So this is quite slow diffusion process if there is a diffusion process. So we don't know what is now exactly diffusing into it and induces this superconductivity. So films were stored in a normal desiccator, and some films were stored in air, and both show the same result. So the storage is not the difference. But here we see signatures of a 2D superconductivity, and this means that the barium 122 layer is quite too thick for having 2D signature, so we assume that the 2D signature appears in the upper samarium iron oxynictide.
Thank you very much. A very interesting result. I have another short question. You mentioned the roughness, about the roughness at the final part. Do you find some change in physical properties?
Pardon?
I mean, depending on the surface roughness, Do you see some change in physical properties like resistivity or
Oh,
something?
these films are barium 1 to 2, so they are undoped and they are not superconducting. So these films were not measured because of superconductivity. So here, this is only made for the surface study.
Ah, I see. Okay.
So these are non-superconducting films.
Okay. Okay, I understand. Thank you.